t, it is a function of a time, and also this q is also given to equal to q of t, right? And this also belongs to this polynomial minus 1 and 1, which is a limit, and it is given that p comma q, which is a representation of inner product between p and q, it is given with the some constant in the questions, and that is equal to, this is minus 1 to 1, and this is p of t into q of t into dt. And it is also given that verify this as inner product, this is an inner product IP on P3 minus 1 and 1 when the set of A vectors is given as 1 comma t square minus 1 by 3, and this is t cube minus 3 by 5t. So anyway, this is a complete big questions, and obviously the solution of this big question is also going to be the large. So we have to make a, as I said you before, that we have to make a pair here, and then we have to check with this given conditions. So obviously we will you see that this inner product, now this inner product will, the respective elements will not be multiplied to each other. We have to apply this given condition, and then we have to integrate each time, and then we have to find the inner product value, right? So probably if I make a pair, so one pair will be 1 dot t, and another pair will be 1 into t square 1 by 3, and another pair will be 1 into t cube minus 3 by 5 into t. So what we will do is that we will apply separately these conditions for this distinct pair, separately these conditions for the distinct pair. How? Let us see how. So for example, if I am writing, see, this is 1 into t, so we will apply that condition which is equal to, in the given, that is equal to minus 1 into 1, and that is t into dt. So we will integrate this t with respect to this limit 1 and minus 1, so that is nothing but that is t square by 2, and you can apply this minus 1 and 1 limit, and you can calculate the value, right? So this is as is after that. Again you can apply this the two distinct pair, that is t square 1 by 3, which is equal to, again you have to use that condition which is given in the questions. So this is t square minus 1 by 3 into dt. So everywhere you have to apply the conditions of the given questions which is given in the inner product, and you have to get the respective integration value every time. But apart from calculating all this, we as we know that we have a set which is equal to, this is 1 comma t, and this is t square minus 1 by 3, and this is t cube minus 3 by 5 into t. So ultimately the story does not finish here. We have to make another pair. We made a pair of 1 with everyone, so we have to make a pair of t with the other leading one, and we have to also make a pair of this one with other leading term, and also ultimately at the last we will make a single distinct pair with this one. So what I mean to say is that we have calculated the distinct pair inner product value of 1 with respect to everyone through that just above. So what we have to make another pair, that is t into t square minus 1 by 3, and again you can apply the inner product the constant that is given in the question, and you can integrate and you can find the value. Similarly you will apply this t into t cube minus 3 by 5 into t, and then again you can use the given constant, and you can find the integration, you can calculate the value, right? So the ultimately this is the second line of making a distinct product, and so third step is making a distinct product of this one with the leading one. So this is t square 1 by 3 into t cube minus 3 by 5 into t. So ultimately again we will simplify these two terms, so ultimately we will get highest power of t raised to 5, and then again we can use these conditions which we have seen in the integration which is given in the question, and we will apply that everywhere, and we will also calculate this value, right? So you will get some finite value here as well, and the only last element is left, so we cannot make it any pair with anyone, so we will simply calculate that value, and that will be simply t cube minus 3 by 5 into t into with respect to dt, and giving the limit -1 to 1. So ultimately this all different values of making the pair, you will get some values, right? And we are checking whether that is orthogonal or not. So everywhere whatever after integration and whatever value, if you get everywhere after integration, if you get the value 0, so that means that distinct pair of vectors are orthogonal. Otherwise, if the value is not equal to 0, value equal to not equal to 0 after integration, what you get from here and here and here, then that is not in an orthogonal vectors. Understood? So this is the concept, that whether it is a matrices, whether it is a normal vectors, we always need to suppose that it is equal to the value 0, then only we can say that it is equal to orthogonal. And you can ask me question why it is 0. So probably if you apply this concept of the limit here or integration, you get this 0. Or since you know this is u into v, and this is a inner product, but I said just before now this is like a dot product. So the very basic simple notion you have studied in class 11 and 12, that this is also represented by this u and this is v and into cos theta. So just before I said you that if any two vectors are orthogonal, the only reason that after calculating even the value comes 0, the basic reason is that the theta is 90 degree. And just before few pages I said you, when the angle between the two vectors are 90 degree, then that is called orthogonal vectors, right? So because of this cos 90, you know it is 0. So ultimately whatever value of modulus u and modulus v it is there, we always have that inner product value as a 0. And this is the main reason this we are saying that if the value is 0, then we conform with the our signature that is an orthogonal vectors, otherwise it is not. So moving on to the next part. So what is a Graham Schmidt process? Okay, so this is the important part of this lecture, which I told you in the beginning as well. Graham-Schmidt orthogonal process. So anyways, here we have a very different ways of calculating. For example, if you are a given set of vectors, that is x1, x2, x3 and x4, similarly, so it could be, if it is up to x4, we can say this is represented in the Euclidean space of R⁴, that is it is going up to the 4 order. Or if it is represented by this way, so that is x1 comma x2 comma x3, so I can say this is an Euclidean space of order r cube, right? So similarly, what we have to do, we have to find, or we have to generate a new vectors, which could be any variable, which could be y or which could be w, anything what you suppose. We have to generate new vectors for using this all given vectors. Then the new vectors that is generated will be called as an orthogonalization of this given vector, and that is what this Graham-Schmidt process says about. So let us talk about that process in the complete manner. So for example, if I write this formula, y2 equal to x2 minus x2 into y1, and this is norm of y1 whole square into y1. So this part is called the projection of, this part is called projection of y1 on x2. Similarly, you can also see through geometrical figure that how the projection is happening and that projection is getting subtracted from the given vectors, and this is the process we convert the given vectors into orthogonalized vector, or you can say we, using the projection formula, we are converting the given vectors into the orthogonalized vectors. So probably this is the simple theory wherever you use, or if you calculate y3 again and the simple value, that is y into x1, and that is your calculated value of y1. So if you are needing calculating for the third vector, that is for x3, so that will be x3 minus x3 into x1, sorry, y1, divided by modulus norm of y1 whole square, my y1 minus x3 into y2 norm of y2 whole square and y2. So probably what I mean to say by this equation is that every succeeding generation of the vectors is involved with the projection of the predecessor vectors. You can see this predecessor vectors y1 and this predecessor y2, whatever we are calculating before, we are also using that for the generation of the next orthogonalized vectors, right? So similarly, if I can give a general notation of this one, that is, this is yi equal to, this is xi minus xi into yi minus 2, and this is yi minus 2 whole square, and this is yi minus 2. So similarly, you can notate, you can give this notation for this x3 as well, and you can find the given orthogonalized vectors. So but this whole theory, what we have done here, is only understood when we do the real examples and when we solve the numericals, and then we are able to understand how this process are really applied, right? So let us see the real examples, and then we can understand more about this Gram-Schmidt process, or this orthogonalization process. So I give you a very common example which is coming every time in GTU. So let me talk about that. Anyways, I forgot to mention that I said you that any two vectors are orthogonal if the angle between that vectors is pi by 2, or if the value of the inner product is 0. So what is an orthonormal then? So just before that, I said that if u and v is any vectors which belongs to the vector space V, then the length of u which is equal to 1, or the length of v which is equal to 1, then these are called orthonormals, right? And this is there again a few questions which comes just to check whether we can generate orthonormal vectors from the orthogonal vectors or not. So you have to apply this concept, and you can similarly go on. So but my focus, as I said, is that we would like to generate orthogonalized vectors from orthogonal vectors, and how we can calculate orthogonalization process using that Gram-Schmidt process. So let us see actual real example of that process, and I am giving an example which is given here. Use Gram-Schmidt process to orthogonalize the set x square minus 1, x plus 1, and x minus 1. So we have been given these three vectors, that is x square minus 1 and x plus 1, and this is x minus 1, as three vectors, and we have to orthogonalize this given set using this Gram process. Okay, so as I said in the and our inner product is defined by this function f into z equal to, so it means that we have been given a constant just like before we have seen. So this is f of x into g of x into dx, right? So this is a given constant. So wherever we use this inner product between the two vectors, or if we make a pair, or if we make a projection of the given set of vectors, what we have seen in this formula, that is this before, if you use this projection formula, then we have to use this constant as well when we are actually calculating the inner product value. So what is our x1? So I can say this is our x1 values, and this is our x2 values, and this is our x3 values, right? So we can simply calculate and our y1, and that our y1 is simply nothing but that is equal to x1, which is given equal to x square minus 1, right? So and this is our calculated value of y1, which is one of the orthogonalized vectors from the given orthogonal vectors. Okay, so for calculating y2 we have to use the formula of a projection, and that is x2 minus this is x2 into y1 and norm of y1 whole square into y1. So basically before calculating this y2 we have to calculate this whole projection. How? So we have been given this x2, right? So this is x2 equal to x plus 1, and we have been given this y1 which is equal to x square minus 1. So we know this is y1 and this is equal to x square minus 1, but we have been given a constant in the given question which is equal to this one. So we have to use this constant and we have to integrate it, and then we have to find this y2 value. So how? So basically I can say this x2 is nothing, or you can say this y2 from here. You can say this y2 equal to, we have been given x2, that is x plus 1 minus and x2 into y1. So before putting into that formula we will calculate x2 into y1. So x2 into y1 is equal to what? So this is x plus 1 into x square minus 1, similarly as like f into x into gx, and the given limit is minus 1 to 1, and we will integrate with respect to dx. So obviously we can simplify this is further. So this is minus 1 to 1, and this is x cube, and this is minus x, and this is plus x square, and this is minus 1 into dx. So we have to integrate this whole one. So this is what. So if you integrate, you further get this is x raised to 4 by 4 minus x square by 2 plus x cube by 3 and minus x, and we can just apply the limit value which is equal to 1 by 4 minus 1 by 2 plus 1 by 3 and minus 1 into, or another value